In the heart of the night, when the air seems to hold its breath and the sounds of the earth fade until they dissolve, one may feel that the sky is not merely a ceiling of stars but a living organism, speaking in deep silences. Some of these silences arise from regions where even light cannot utter a word, black holes. They are not simply objects, they are processes, relationships, states of matter and gravitational fields pushed to their limits. When a massive star collapses, it doesn't just become dense, it bends space-time so severely that it carves out a region from which nothing can ever escape. The boundary of this region is the event horizon, defined, if non-rotating, by the Schwarzschild radius, which for a solar mass black hole is about 3 kilometers. Compress the sun to the size of a city, and you get a well from which not even a photon can find its way back. Deeper still, general relativity predicts a singularity, a point where physical quantities would diverge. It signals that our theory, triumphant on cosmic scales, calls for help from quantum mechanics. From this conceptual short circuit arises the enigma. How can an event horizon that swallows information be reconciled with the quantum principle forbidding its destruction? Stephen Hawking showed that black holes are not completely black. They radiate like thermal bodies, with temperature inversely proportional to mass. This leads to a paradox. If the evaporation is thermal, the information of the degrees of freedom that fall in seems to vanish. Bekenstein, even earlier, had attributed to the black hole an entropy proportional to the area of its horizon, not its volume, a powerful clue that nature encodes information on surfaces, as the holographic principle suggests. Holography, made concrete in the ADS-CFT correspondence, indicates that a gravitational system in one space can be equivalent to a quantum theory without gravity on a lower dimensional boundary. If gravity is holographic, information is not lost but spread across the horizon and can, in principle, re-emerge in the radiation, following the so-called page curve. It's a fascinating framework, supported by calculations in simplified models, yet it clashes with other conjectures, such as the quantum firewall proposal. Highly energetic barriers at the horizon that preserve unitarity but violate the local experience of a falling observer. Here, physics offers no single verdict. Each hypothesis saves some principles while straining others. The observational reality, however, is less silent than one might think. Gravitational waves recorded by LIGO and Virgo have revealed mergers of stellar mass black holes, typically tens of solar masses and sometimes even larger, likely the result of hierarchical mergers in dense environments. We know that supermassive black holes dwell in the centers of galaxies, millions or billions of times heavier than the Sun. Our Milky Way hosts an object of about 4 million solar masses. We do not see the black hole itself but the effects on the gas plunging toward the horizon, which can heat to extreme temperatures, forming accretion disks and relativistic jets thousands of light-years long. The first indirect photographs of these giant shadows, obtained through planet-scale interferometry, gave the world a silhouette, a luminous ring framing a dark cavity, just as relativity predicted. The size and shape of that outline are consistent with an event horizon. It's not definitive proof of a singularity, but an observational seal of the extreme gravitational regime. Meanwhile, the search for intermediate mass black holes, hundreds or thousands of solar masses, suggests a richer zoology. Traces in globular clusters, signals of coalescence, and dynamic hints open the catalogue of a family once elusive. Their role in assembling supermassive monsters remains one of the most intriguing open questions. Are they primordial seeds, remnants of population 3 stars, or products of merger chains? Each answer changes our cosmic story. From a theoretical point of view, the desire to bend the tyranny of distance has fueled the idea of Einstein-Rosen bridges, corridors connecting distant regions of spacetime. In the classical formulation, however, these bridges pinch off too quickly to be traversable. No traveler could cross alive. To make a tunnel traversable requires exotic matter with effectively negative energy density, capable of holding the throat open against its natural collapse. Quantum physics admits locally negative energy phenomena, like the Casimir effect, but in minute quantities. Turning these effects into cosmic infrastructure remains, for now, refined science fiction. Nonetheless, speculative thought has pushed the boundary further. The equals EPR idea, linking quantum entanglement, EPR, to wormholes, suggests that pairs of maximally correlated systems might be connected by non-traversable micro-wormholes. If entanglement is woven into the fabric of spacetime, then reality's architecture could be a web of correlations rather than building blocks. In other research lines, loop quantum gravity hypothesizes that collapse does not end in a singularity but in a quantum bounce. The resulting object, a Planck star, would release information over immense timescales, softening the paradox. String theory, on the other hand, has proposed scenarios such as fuzzballs, no longer an empty interior surrounded by a smooth horizon, but a tangle of microstates extending to the horizon scale, where information is not lost because there is no inside for it to vanish into. All these ideas have subtle observational consequences, often beyond our current sensitivity, yet they provide conceptual maps for searching for imprints. Modified Hawking radiation spectra, echoes in gravitational waves after mergers, statistical deviations in stellar motions around galactic monsters. The allure of black holes lies not only in their power of destruction but in their thermodynamics. Temperature, entropy, area, laboratory words that find meaning on cosmic horizons. The fact that entropy is proportional to area rather than volume has inspired the idea that fundamental physics measures surfaces. The second law of black hole mechanics predicts that the total area of all horizons cannot decrease in classical processes, a nearly poetic parallel to the growth of entropy in thermal systems. Yet Hawking radiation, with its slow drizzle of particles, allows for a reduction in area, accompanied, however, by an overall increase of entropy outside, preserving the arrow of time. If the page curve indeed describes the evolution of the von Neumann entropy of radiation, rising, reaching the maximum, and then falling as information returns, then even the bleakest evaporation is, in principle, reversible at the informational level. Conceptual traps remain. The equivalence principle, cornerstone of general relativity, says that a freely falling observer should notice nothing extraordinary when crossing the horizon. Quantum unitarity, on the other hand, seems to demand a firewall that would deny this experience. The conflict is not merely technical, it's a window into how nature reconciles continuity with granularity, geometry with information. Into this already dense picture enters the question that broadens our perspective. What if intelligences older than ours had already explored these limits before us? The Kardashev scale classifies civilizations by the amount of energy they control. Type 1 for a planet, Type 2 for a star, Type 3 for a galaxy. For a descendant of ours even approaching Type 2, the energies at play in accretion disks or stellar magnetospheres would be resources, not hazards. There would be no need to imagine spaceships of steel hulls, only local curvature engineering, manipulations of the refractive index of quantum vacuum, configurations of fields on scales currently unimaginable. If traversable wormholes require matter with negative energy, those who master strong quantum conditions might catalyze regions where the quantum inequalities limiting such energies are temporarily squeezed within allowed bounds. It is a hypothetical language, yes, but closer to physics than to sorcery. It speaks of constraints, quantities, instabilities, and how to mitigate them. Above all, it suggests a change of perspective on travel. Perhaps one does not move through space but restructures space around the traveler, compressing distance ahead and expanding it behind, as in Alcubierre-type metrics, which locally respect relativity while demanding prohibitive energy ingredients. If such architectures remain mountains to us, they could be hills to those with a million-year head start. The operational question, then, is not whether nature allows it. The mathematics already leaves cracks open, but how much it costs in energy, and how much stability can be achieved before quantum fluctuations tear the corridor apart. And even if the answer were too much, the extraordinary power of black holes remains. As instruments, chronometers for testing strong relativity, laboratories where magnetized plasma dances at relativistic speeds, proving grounds for high-energy physics in contexts no accelerator can match. The path, in any case, extends beyond the first conceptual horizon, because black holes, when you look closely, do not end at their silhouette. Their environment is a theater of phenomena that narrate the story of galaxies. Relativistic jets emitted from some active nuclei influence star formation in their cosmic neighborhoods. They heat gas, blow away material that would otherwise feed new stars, carve cavities in intracluster media. It's a feedback that links the growth of the black hole to that of its host galaxy. The more the central monster feeds, the more it regulates the diet of the stellar community around it. This dance of cause and effect can be read in the observed correlations between black hole mass and the velocity dispersion of stars in the galactic bulge. These are not academic details. Without such cycles, the visible universe would have a different face. Even cosmic chemistry is entangled. Winds and jets enrich the intergalactic medium, seeding heavy elements far from stellar nurseries. In this sense, black holes are not merely the ends of stellar evolutions but engineers of cosmic landscapes. On the microphysical front, the idea that information is never destroyed has subtle consequences for how we imagine the interior. If fuzzballs replace the classical image of a smooth horizon, then an observer falling in would encounter a quantum structure diffused up to the horizon scale, a sea of microstates. If instead a quantum bounce avoids the singularity, the collapse could transform, over timescales immense compared to ours, into a late emission that returns part of the information, perhaps as transient signals. Some have speculated about echoes in gravitational waves after mergers, faint interferences betraying the presence of reflective surfaces instead of perfect horizons. So far, analyses have not produced consensus, but the attempt to stitch phenomenology between microstates and macroscopic signals is a powerful stimulus. It imposes falsifiable predictions and forces hypotheses to take risks. Even concepts like cosmic censorship, the conjecture that nature hides singularities behind horizons, preventing gravitational nudity, are tested in extreme scenarios, such as rapid accretion or subtle perturbations of rotating black holes. Each observation that tightens the net refines the space of theories. Then comes the question of navigation. Imagine wanting to use a black hole instead of avoiding it. Orbital mechanics around a compact rotating object offers a range of exotic trajectories. Photon orbits, unstable paths for massive particles, trajectories skimming the speed of light and returning photons, boosted in energy through gravitational scattering. A sufficiently advanced intelligence could use these effects as extreme slingshots to accelerate miniaturized probes, perhaps entangling them into quantum communication networks. On the energetic side, a rotating black hole stores a fraction of its mass in spin energy. Processes like Penrose extraction or superradiance for light bosonic fields allow, in principle, for its recovery. It's difficult, but not magic, its rotation being drained, geometry returning work. On more terrestrial scales, laboratory analogs, superradiant fluids, waves in rotating basins, have even verified miniature versions of these effects, reminding us that extreme physics echoes in our tanks and condensates. Every analogy is imperfect, but pedagogically powerful. It teaches us what ingredients are required and how to recognize them. When the conversation turns to alien visits, it's worth distinguishing imagination from methodology. That unidentified aerial phenomena exist is a trivial fact. Unidentified does not imply extraterrestrial. Still, idea by idea, physics provides a language for discussing hypothetical unconventional technologies without descending into arbitrariness. If an object seems to move with impossible accelerations, an explanation need not violate the speed of light. It suffices that the frame of reference be deformed, that the medium in which the object moves is not our flat space but a bubble of altered metric. Inside, the vehicle would not experience unbearable accelerations. From the outside, its trajectories would appear abrupt. Methods for creating such bubbles are, for now, beyond our reach, not only because of the required energy, but because of stability. Small quantum fluctuations could destabilize the entire configuration. Yet, through controlled heresy, one can imagine cultivating tiny regions where vacuum energy is manipulated, perhaps by exploiting metamaterials or coherent states of the electromagnetic field. These scenarios temper enthusiasm with quantitative constraints. The energy scales, pressures, and tensions required are so astronomical that the examples remain mental constructs. But this accounting is valuable because it transforms miracle into budget, desire into project. Not can or cannot in the absolute, but what would it take, and how much? Here the multiverse enters as a metaphysical horizon, with physical legs. Some versions of inflationary cosmology predict eternal inflation, generating causally disconnected regions with differing physical parameters, bubbles in a metastable sea. Other incarnations, such as the string theory landscape, offer an immense plurality of potential minima, each with its own constants. In such frameworks, black holes might be not only outcomes but also generators. Scenarios in which a collapse, instead of ending in a singularity, buds into a child universe through a bottleneck. Causality in the parent region would remain severed. No signal could return to tell the tale of the birth. Yet the idea that the universe might reproduce itself initiates a kind of cosmic biology, in which the selection of parameters is not teleological but statistical. Regions whose laws favor black hole formation generate more descendants, and so on. It's a bold and controversial hypothesis, but it illuminates the imagination with a falsifiability criterion. If true, one might seek specific correlations between physical constants and the abundance of black holes. So far, we have no evidence, but the idea that the cosmos might evolve parametrically has fertilized discussions that would otherwise remain metaphysical. Weaving the unknown into an observational narrative is the art of modern astrophysics. Take the disk of gas dancing around a black hole. Spectral lines broaden and shift under Doppler effects and gravitational redshift. Hot atmospheres emit X-rays modulated by magnetorotational instabilities. Turbulence feeds a tree of quasi-periodic frequencies. By measuring these signatures, one extracts spin parameters, inclination, disk geometry. In galactic binary systems, small variations in luminosity reveal vampiric matter transfers. In other cases, a black hole snacks on a passing star, producing tidal disruption events that flare for months. These are natural laboratories teaching us how to read a shadow. On the gravitational front, the merger spectrum, in spiral, merger, ringdown, bears the signature of quasi-normal modes. Frequencies and dampings that depend only on mass and spin, as though every black hole rang a universal gong. Verifying that these tones match predictions is a deep identity test. If they differ, we might be facing exotic compact objects, ultra-dense quark stars, false vacuum bubbles, or microstate remnants. The next step is the multi-messenger symphony. When an active nucleus flashes in gamma rays and, almost simultaneously, a new high-energy neutrino signal arrives from the same direction, the hypothesis that a jet aligned with our line of sight is accelerating protons becomes tangible. If, in the future, more sensitive gravitational wave detectors capture mergers at currently invisible frequencies, we will be able to map the assembly of supermassive black holes beyond the redshift of the first galaxies. Each new messenger, photons, gravitons, neutrinos, cosmic rays, adds a channel of inquiry and cross-verification. In parallel, laboratory experiments continue to probe quantum vacuum with ever finer precision. Tiny deviations, instabilities, or squeezed states might one day suggest pathways for rendering currently speculative ideas operational, such as confining negative energy concentrations in stable regions. The path is not linear. It is rather a mosaic where theoretical and observational tiles align unexpectedly. In the end, black holes teach us two lessons, apparently opposite yet profoundly complementary. The first is humility. When geometry bends beyond common sense, many intuitions crumble, and one must let the equation lead, not the analogy. The second is audacity. Equations, when questioned without fear, admit solutions that resemble science fiction tales, wormholes, energy extractions from rotation, bridges forged from entanglement. It is within this tension that science lives and narrative becomes a bridge between what we know and what we dare to imagine. Perhaps one day we will understand that the event horizon is not a curtain that closes, but a surface that writes, a register of information, an interface between space-time and quantum theory, a place where reality reinvents itself. If so, the image of travel will change, not crossing distances, but altering relationships, not pushing a shell through the void, but tuning fields and geometries like instruments. And in that renewed lexicon, the idea of not being alone, not only as a species but as a universe, will cease to be a shiver and become a calculation. Until then, every photographed shadow, every gravitational echo, every ring of light around darkness will remind us that beneath the skin of the sky lies a palimpsest of possibilities, and that reading it requires patience, courage, and a curiosity bold enough to cross horizons. If you've come this far, it means you love curiosity as much as we do. If you enjoyed this journey, leave a like, write a comment, and subscribe to the channel. It's the best way to support what we do. Your presence truly makes a difference. Until the next exploration.